All right, let's talk about a true hero element. Seriously, it's in the pencil you use, the food you eat, the clothes you're wearing. It's even in the very cells that make you, well, you. We're talking, of course, about carbon. Let's dive in and see what makes this element so special.
Think about it. Carbon forms the foundation for millions of different compounds, way more than all the other elements put together. So here's the puzzle. If carbon is so essential, the very backbone of life itself, why is it actually so incredibly rare on our planet?
Get a load of this number, 0.02%. That's it. That is the teeny tiny fraction of the Earth's crust made of carbon minerals. In the air, just about 0.03%. So, how does this ridiculously scarce element become the absolute star of the show? Well, the secret is all about how it makes friends.
So here's our game plan for today. We're going to uncover the secret to how carbon bonds with other atoms, reveal its two amazing superpowers, meet its huge family of compounds, and then we'll see it in action in a way you probably deal with every single day.
Okay, it really all starts with bonding. See, the secret to carbon's magic isn't about giving orders or taking things from other elements. Nope, it's about something much more cooperative.
You see, carbon's kind of stuck. It's got 4 electrons in its outer shell, but it really wants 8 to feel stable. Now, it could try to just get rid of those 4, but that would take a massive amount of energy. The other option? Try to steal 4 more. But its nucleus, with only 6 protons, just isn't strong enough to hold on to 10 electrons. The whole thing would just fall apart.
Most elements solve this problem with what we call ionic bonds. It's a simple give and take. One atom donates an electron, another one accepts it. Easy. But since carbon can't really do either of those things, it came up with a brilliant third option: sharing.
And this is what we call a covalent bond. Instead of a tug of war over electrons, it's more like a firm handshake. Both atoms agree to mutually share electrons. And by doing that, they both get to count those shared electrons and voila, everybody's stable and happy. And this sharing isn't a one-size-fits-all deal. Sometimes atoms share just one pair of electrons, making a single bond, like you see in hydrogen. Sometimes they share 2 pairs, creating a double bond, like in oxygen. And sometimes they form a super strong triple bond, sharing 3 whole pairs, like in nitrogen.
Okay, so this whole sharing thing, this ability to form covalent bonds is what unlocks carbon's 2 incredible superpowers. And these are the real reason it can create literally millions of different compounds.
Superpower number 1 is catenation. Now that's a really fancy word for a simple idea, linking up with itself. Carbon is exceptionally good at forming strong, stable bonds with other carbon atoms. Because it's a small atom, its nucleus keeps a really tight grip on those shared electrons. Other elements, like silicon, try to do this, but their bonds are just weaker and less stable. And look what this does. Because of catenation, carbon atoms can link up like Lego blocks. They can form long, straight chains, they can create complicated branch chains, and they can even loop around to form super stable rings. This right here is the reason we have such a huge diversity of organic molecules.
All right, on to carbon's second superpower, tetravalency. Tetra just means 4. So this means every single carbon atom has like 4 hands. It can form 4 covalent bonds at the exact same time. It can link up with other carbons, or it can bond with a whole variety of other elements: hydrogen, oxygen, nitrogen, you name it.
So, when carbon uses these superpowers to bond only with hydrogen, it creates the simplest, most fundamental family of organic compounds out there, the hydrocarbons. And this family is basically split into 2 main branches.
This table lays out the difference perfectly. On one side, you've got saturated hydrocarbons, also known as alkanes. They only have single carbon-carbon bonds. We call them saturated because they're holding on to the maximum number of hydrogen atoms possible, which makes them pretty stable and less reactive. On the other side, you've got the unsaturated folks, alkenes with double bonds and alkynes with triple bonds. Those extra bonds make them way more reactive.
And you can actually see this difference in reactivity with a simple flame test. It's pretty cool. Saturated compounds, the alkanes, they tend to burn really cleanly with a nice blue flame. That means complete combustion. But the unsaturated ones, with their higher carbon ratio, they often burn with a sooty yellow flame because they don't combust completely.
Okay, with millions and millions of possible compounds, how on earth do scientists keep track of them all, right? They can't just give them all cute nicknames. They needed a system, a logical, official way to name every single one. And that system is called IUPAC nomenclature. It basically works like a three-step recipe. First, you figure out the word root based on how many carbons are in the main chain, like meth for 1, F for 2, prop for 3, and so on. Second, you tack on a suffix for the bond type, ane for single, in for double, ine for triple. And finally, you add little bits to the name for any special guests attached to the molecule. These special guests are called functional groups, and they are total game changers. They're specific little clusters of atoms that can replace a hydrogen, and when they do, they completely change the molecule's personality and its properties. For instance, if you stick an O8 group on there, you've just made an alcohol, and you add the suffix -ol, like in ethanol. Other groups can create totally different things like aldehydes, ketones, and acids.
All right, enough theory. Let's see how all this amazing chemistry comes together to create something we all use every single day. Let's put carbon's superpowers into action and talk about the science of soap.
You know, it's a question we probably never stop to think about. We use soap to wash away oily, greasy stuff that water, on its own, just can't handle. So how does this humble little molecule pull off this cleaning magic trick?
The secret is that a soap molecule is literally two-faced. It has a hydrophilic head, that means water-loving. It's an ionic part that's totally attracted to water. But then it has this long, hydrophobic tail, water-fearing. And what is that tail made of? A long hydrocarbon chain. It hates water, but it absolutely loves oil and grease.
So, when you mix soap with water, these two-faced molecules do something incredible. They automatically arrange themselves into these tiny spherical clusters called micelles. All the oil-loving tails point inwards, grabbing a piece of grease and trapping it in the center. At the same time, all the water-loving heads face outwards, forming a protective shield.
So here's the play-by-play of how it works. The soap molecules swarm a piece of oily dirt. Their long carbon tails dive right into the oil, latching on tight. This is what forms the micelle, with the oil now trapped safely inside. And because the outside of this micelle is water-loving, when you go to rinse, the water just grabs the whole package and washes it right down the drain. Gone.
And this all comes back to carbon's superpower of catenation, that amazing ability to form long, stable chains. That hydrocarbon tail is the key. It's the bridge between the world of oil and the world of water. So from a super rare element in the Earth's crust to the hero that helps keep our world clean, carbon really is the foundation of just about everything. Makes you wonder, what other everyday marvels are made possible by this one simple, powerful element?